And usually fancy equals hard. It's nothing at all, apparently. Ay, ay, ay. It's been happening all day. That's not true. It happened like twice. Yeah, it's just basically saying that you're going to take the derivative and then take the derivative again. So how hard can that be? Well, it could be really hard or it could be really easy depending on the nature of the function. The thing is, if you remember when we were talking about quotient rule and product rule, I said that it's a pretty rare instance where I'm going to ask you to simplify your answer. It's going to be find the derivative. And then we can leave it like this. It's a big old mess. It's all right to leave it like that? I'm like, yeah, sure. Because when you get to cases where you have to find a second derivative, it's in your own best interest to simplify it a little bit before you move on. Otherwise, you have a big mess on your hands. And in fact, you could have, after you take the first derivative, something that involves, if you were going to take the second derivative, product rule and quotient rule and something called chain rule, all mixed in together in one problem. But if you simplify it down a little bit, maybe it's just power rule, right? So it's in your own best interest to think about doing stuff like that. I'm very rarely going to tell you to do that. All of this stuff in the table is just notation. It's to familiarize you with notation, get you kind of up to snuff on that. The first derivative, we're kind of used to this for the most part. Y prime dy dx, we work with that a lot. This capital D sub x of y also stands for derivative. Odds are, if you see the letter D in this course, it stands for derivative, regardless of what the context is. Right? But this is something that we don't very often use, but it comes up from time to time. F prime we've used, and the d dx of a particular f of x or a y, that's come up. But then if you look at the second derivative, it follows the same structure. Double prime, powers of 2. But it's basically the same stuff, right? It only starts getting weird when you're dealing with the primes after a triple prime, because, I mean, if I ask you to find the 99th derivative, which comes up, I think, in the third example, like, well, do I keep putting little tick marks here? That's a lot. Instead, you put it in parentheses as you would write a power, but put it in parentheses so that there's no confusion. We don't want people thinking that you want the 99th power of the function y. We want the 99th derivative, so the parentheses is just shorthand way of indicating that. All right. So that's all this table is telling us to do. Actually, it's not even telling us to do anything. It's just kind of gearing us up for when we are told to do something. So in the first example, you see 12 times the cube root of x. The first thing I would do is rewrite that as 12x to the 1/3. And then take the derivative of that. What is the derivative of 12x to the 1/3?
4x
To the negative 2/3. Yep, subtracting 1 from the given exponent. All right, so I need the second derivative, so I take the derivative of my derivative. All right, so what is the derivative of 4x to the negative 2/3? X to the negative 5/3. We're subtracting 1 from the power every step of the way, but sometimes with fractions that can be troublesome. If the denominator is 3, you're really just subtracting 3 from the numerator. So if I needed to do it again, it would be negative 8/3, and negative 11/3, negative 14/3, and so on. Right? So a little shorthand way of doing it, just subtract the denominator from the numerator.
Wait, how'd you get negative 5/3?
Subtracting a 3 from the negative 2.
Okay.
Yeah, because it's the same as subtracting 3/3 from the negative 2/3. All right, so h prime of t, first derivative. What's the derivative of 4 sine t? Well, what's the derivative of sine? Cosine. So it's 4 cosine t. Minus 5, and what's the derivative of cosine? Negative sine of t. So you could do it all in one shot if you want. Make it 4 cosine t if you see it. Oh, not cotangent, cosine of t. It looks like cost. Hold on. Plus 5 times the sine of t. I mean, if you write it without the parentheses, I know you're not saying cost, so it's fine. It's just I've had people say in the past, how do you know cost is involved in this? And we're like, oh, you know, deeper problems here. All right, so second derivative of cosine t again is negative sine of t. So if I multiply that by 4, it's negative 4 times the sine of t. And what's the derivative of 5 sine t?
5 cosine t.
5 cosine t, exactamundo. All right, so a little trickier when it involves trig, but I mean it's not tricky yet. Pretty good. It's not overwhelming if you're dealing with simple trig functions, but if you're dealing with more complicated ones like a trig function raised to a power, or maybe a trig function of something other than t, you know, maybe like a trig function of a log function or something like that, then it can get a little crazy. But for now, we'll keep it simple. The 99th derivative. All right, so this should take us like the rest of the period, I guess. And I left you just so much room for it.
Isn't it just going to flip back and forth?
Yeah, exactly. So let's start off with the first derivative. K prime of x would be what? Cosine of x. The second derivative? Negative sine x. Third derivative? Negative cosine of x. And the fourth derivative? Sine x. That's actually where we can stop, because at this point we've completed one full cycle. I mean, if you need to prove it to yourself, you can. You could just keep going, maybe do a fifth derivative and see that that gives you cosine. Sixth derivative will give you negative sine, and so on. But it's going to bounce back and forth, well, bounce among these 4 possibilities. First derivative, second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th, 11th, 12th, and so on. Every multiple of 4 in terms of derivatives is going to have a result of sine of x. So I can kind of go from there. Oh, that is not the sliding thingy tool that I was looking for. That's a tool, all right. Let me do the 100th derivative. That would be what? Sine x, because 100 is a multiple of 4. All right. So this corresponds to this. So if I'm looking for the 99th derivative, I just take one step back.
Is 4 always a full life cycle? Or a
Yeah.
full cycle, not a cycle?
I knew what you meant.
Come on, that's cute. Like, it's a life cycle of a
Technically,
sign.
1 is like a multiple of everything, so how do you know that it's not just cosine?
I missed the beginning of what you said because I was
So
still
like
laughing.
1 is a multiple of everything.
1 is a multiple of everything. Yeah, these are actually remainders, as it turns out. So when I get to the 5th derivative, that's 1 past a multiple of 4. The 6th derivative will be 2 past a multiple of 4, and so on. So
Right.
we're using the 4th derivative as our benchmark,
Okay.
and then going back.
But
and
how
forth
would you
from there.
know if it wasn't, like, how would you know that it's not like the first one?
Because it goes in a pattern of 4.
Yeah.
Right.
technically cosine is a multiple of the 99, but like thinking about the way that the cycle goes, you're just gonna have that and then another and another and another. So like you have to think about how do you get to the final number, which would be 100. Right? It's not like the final number, but like the closest number to it.
Another way, I mean, that's the intuitive way of thinking about it, and that's the way I thought about it. But I suppose you could also look at it as if this is a multiple of 1, that's not overly helpful, but multiple of 2, multiple of 3, that could be more helpful. Multiple of 3 is probably more helpful because 99 is a multiple of 3. And so whatever value is a direct multiple of a particular number you're looking for. It's just a little trick when you're looking at these two, because if it's a multiple of 2, it could also be a multiple of 4. So which is it, you know? So it's kind of like you're attacking it from both ends. So what I do personally is I always find out where the multiples of 4 are and then work backwards or forwards from there. Thanks.
So what if it's like the 24th derivative, right? Because that's easily divisible by 2, 3, and 4.
Just think about how those.
So is that, I mean, would I want to use whatever the 4th derivative is, just because that's, like, it takes the least number to get there, if that sort of makes sense?
Yeah, I mean, you can think of it that way, but if you're thinking in terms of full cycles,
Yeah.
that
Have 6 full cycles.
you would have 6 full cycles, and that would get.
So I would use the 4.
Yeah. What I generally I mean, if you want to use your calculator as a resource here, or not, one way to do it would be to divide whatever the number is by the number of units per cycle. You remember powers of I? I, -1, -I, +1. You took whatever the power was and divided it by the number of units in the cycle, which was the same as this, 4 units in a cycle. Whatever your remainder was, that's your placement. So 96 remainder 3 place you into the 3rd unit in the cycle. So you could look at it that way too. I mean, this basically is the powers of I, the same approach, and in fact, it's more than that. This is the connection between trigonometry and imaginary numbers. So, like when you
This is getting really crazy.
I, -1, -I, +1, that it will work out to be equivalent depending on what the x value is. So this is the bridge from one world into the other. It's the port key.